Module 8.1. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 8.1. How can we visually describe the relationship between two or more variables? In previous modules, we discussed how two variables might exhibit a pattern with one another, but that does not imply that one of the variables directly influences the other. It is often the case that we would like to know about the relationship between two variables. In this module, we will look at how to visually describe the relationship between two or more variables. We may want to compare two categorical variables. To investigate a possible relationship between two categorical variables, we use a contingency table. Definition: a contingency table displays the relationship between two categorical variables. The categories for one variable are listed down the left side in the rows, and the categories for the second are listed across the top, columns. Each cell of the table contains the count of the number of cases that are in both row and column categories. Example: suppose a researcher is interested in comparing a person's diet to health outcomes. They decide to compare the Mediterranean diet to the American Heart Association's recommended diet. The following table was published in the article Mediterranean Diet Pattern in a Randomized Trial, published in 1998. Your turn. Look at the table and see if you can identify the following. Then come back and we'll see if you got the right answers. How many people were in the study? There were a total of 605 people in the study. This can be seen by looking in the bottom right-hand corner of the table. How many people developed cancer? This can be seen by looking at the cancers column and the total row. How many people ate the Mediterranean diet? This can be seen by looking at the corresponding row in the total column. How many people eating the Mediterranean diet developed fatal heart disease? This can be found by looking at the intersection of the Mediterranean row and the fatal heart disease column. We can also use a table to calculate different proportions. Definition: a conditional proportion depends on one of the variables having a given value. For example, we may be interested in the proportion of people on the Mediterranean diet who develop fatal heart disease. Here we are conditioning on the person eating the Mediterranean diet since their information is conditional. In this example, they are conditional on diet. The proportion can be calculated as 14 divided by 302 is equal to 0.0464. In situations where we distinguish between an explanatory and response variable, it is natural to form conditional proportions based on the explanatory variable for categories in the response. In this scenario, diet is explanatory. Marginal proportions are calculated using the overall total and are not conditional. The proportion of people who ate the AHA diet is not a conditional proportion. The outcome is not a part of the calculation, and the only counts in the right margin are used to form a proportion, such as the proportion 303 divided by 605. This is called a marginal proportion. For each of the following, calculate the requested proportion and decide if it is conditional or marginal. You may leave your answers as a fraction. Pause the video, and when you come back, we'll look at the solutions. Note that the first two proportions are marginal. Therefore, they are both divided by the total number of cases. The second two are conditional. There are several different types of graphs which can also be used to visualize a relationship between two categorical variables. We could display proportions of outcomes for each diet separately, side by side, or we can combine all of the information into a stacked bar graph. These plots can help us look for associations. Definition: a side-by-side bar graph, the height of each bar is the number of the corresponding cell in the two-way table. So looking here, we see the different outcomes along the bottom for the two different types of diet, both Mediterranean and AHA. A stacked bar chart is like a side-by-side bar chart, but the bars are stacked instead of side-by-side. It appears there is a weak moderate association between diet and health outcome. There would be no association if instead the proportion with different health outcomes would have been equal for each diet. Caution: when sampling from a population, even if there is no association between the two variables in the population, you can expect the sample conditional proportions you can't expect the sample conditional proportions to be exactly the same because of ordinary variation from sample to sample. Later in the course, we'll present inferential methods to determine if observed sample differences between conditional proportions are large enough to indicate that the variables are associated in the population. Definition: a difference in proportions is a difference in the proportion for one categorical variable calculated for different levels of another categorical variable. A difference in proportions is calculated from sample data is denoted as p hat 1 minus p hat 2, where the 1 and 2 distinguish the different groups. A difference in proportions calculated from population data is denoted as p1 minus p2. Your turn. Find the difference in the proportion of people on the AHA diet who develop cancer versus the proportion of people on the Mediterranean diet who develop cancer. We can denote this by p hat A minus p hat M, where p hat A is equal to the proportion of people on the AHA diet who develop cancer, and p hat M is the proportion of people on the Mediterranean diet who develop cancer. Notice that we will use p hats because the proportions are calculated from a sample of people. You should have found the following. In the previous section, we discussed how two variables might exhibit a pattern with one another, but that does not imply that one variable directly influences the other. We looked at ways to summarize two categorical variables with two-way tables, a difference in proportion, and bar charts. In this section, we will focus on exploring the relationship between two quantitative variables. Recall from Module 2, if we want to determine if two variables are related to one another, we must first determine how the two variables may be interacting with one another, i.e. determine if there is an association. We usually identify one of the variables as the explanatory and one as the response. Definitions. The explanatory variable is the variable which will help us understand values of another variable. It is also known as the independent variable or predictor variable. The response variable is the variable we want to observe change in based on the explanatory variable. It is known as the dependent variable, outcome variable, or exposure variable. How can we visualize the relationship between two quantitative variables? Let's review the ICU data set we looked at previously. The ICU data set consists of a sample of 200 subjects who are part of a much larger study on survival of patients following admission to an adult ICU unit, derived from the Homer, Limshaw, and Sturdivant and Friendly papers. From this data set, the cases are each of the subject. The data set includes 20 variables, majority are categorical. Below are the quantitative variables in the data set: age, systolic blood pressure, and heart rate. We are going to focus on the variables age and systolic blood pressure. One question a researcher may be interested in is if older people tend to have higher systolic blood pressure, i.e. is there an association? Further, the researcher may want to know if age can be used to predict systolic blood pressure. In this scenario, age would be considered the explanatory variable and systolic blood pressure the response. A scatter plot is a plot which represents the data from two quantitative variables as points. Each point on the plot represents two values, one from each of the quantitative variables. The explanatory variable is located on the x-axis and the response on the y. Scatter plots are often titled using the following two conventions: y variable versus x variable, or y variable as a function of the x variable. Here we have a scatter plot of systolic blood pressure as a function of age. Notice that the point highlighted represents a subject who is 40 years old and has a systolic blood pressure of 86. Looking at the plot, there does not appear to be an association between age and systolic blood pressure. Recall from earlier, the two variables are associated if the values of one variable exhibit a pattern with the values of another. How can we describe the association we see in scatter plots? When describing the association between variables in a scatter plot, there are three characteristics we need to consider: direction, strength, and form. Definition: we can describe the strength of an association as follows. A positive association means that the values of one variable tend to be higher when values of the other variable are higher. In this case, the scatter plot will go up and to the right. A negative association means that the values of one variable tend to be lower when values of the other variable are higher. In this case, the scatter plot will go down to the right. Two variables are not associated if knowing the value of one variable does not give you any information about the value of the other variable. In this case, the scatter plot has no pattern. Looking at a plot of the ICU data, we do not see an association. Let's look at another example. A sociologist assigned to a correctional institution was interested in studying the relationship between intelligence and delinquency. A delinquency index ranging from 0 to 50 was formulated to account for both the severity and the frequency of crimes committed, while intelligence was measured by IQ. Located in the video script is a table displaying the delinquency index of a sample of 18 convicted minors. Here we have the scatter plot. We can see that the scatter plot goes down and to the right. Therefore, there is a negative association between IQ and delinquency index. In other words, as IQ increases, the delinquency index decreases. We can also describe the strength of an association. When the points are clustered very close together along an underlying pattern, we say that the association is strong. When the points are clustered somewhat close together along the underlying pattern, we say the association is moderate. And when the points are clustered far apart, we say the association is weak. The top row of plots are all positive associations, while the bottom row are all negative associations. In the center, we would have moderate relationships, and as we move to the right, we have strong, and to the left, weak. Looking at a plot of the delinquency data, we can see that the underlying pattern is a line. The points are clustered somewhat close to the line, so we can say that the association is moderate and negative. Associations can take different forms. When the underlying shape is curved, we say the association is curvilinear. When the underlying shape is a straight line, we call the association linear. Linear associations are also called correlations. Looking at the plot of the delinquency data, we can see the underlying pattern is a line, therefore the association is linear. The correlation coefficient is a numeric summary of the direction and strength of a linear association between two quantitative variables. If the correlation coefficient is calculated from sample data, we denote it with the letter R. If the correlation coefficient is calculated from population data, it's denoted with the Greek letter rho. The correlation coefficient will always take values between -1 and 1. The absolute value of the correlation coefficient tells us about the strength. Values close to 0 suggest a weak or no association, while absolute values close to 1 suggest a strong association. The sign of the correlation coefficient tells us about the direction of the association. Negative values suggest a negative association, and positives suggest a positive association. Further, the correlation coefficient has no units of measurement, and if we switch the response and explanatory variable, the value will not change. Looking at the two scatter plots from earlier. Here we have the scatter plot of systolic blood pressure versus age for the adult ICU patients. The Pearson's correlation coefficient R is equal to 0.04 in this case. The value supports that we visually see in the scatter plot, i.e. there is little to no association. Here we have the scatter plot of delinquency index as a function of IQ. Here the Pearson's correlation coefficient R is equal to -0.47. This value supports what we visually see in the scatter plot. In other words, there is a moderate negative association. Cautions. correlation coefficient is only a valid summary when there is a linear association. You must plot your data before computing it to make sure the association is linear. The correlation coefficient is sensitive to outliers. You should plot your data to see if there are any outliers. Recall that an outlier is an observation that lies outside the overall pattern of the other observations. Another way to determine if a plot point is an outlier with respect to a numerical summary is to see if removing the point would substantially change the results of the calculation. The Pearson correlation coefficient is the most often reported when data is continuous, and it is reasonable to assume that the variable has a normal distribution. However, if one of the variables is not continuous or does not come from an approximately normal distribution, the Pearson's correlation coefficient may not be appropriate. A Spearman-Ranks correlation coefficient is appropriate to compare the variables of interest as long as they each have an ordering without any other assumptions. Your turn. Below is a scatter plot which displays the number of abortions performed per 1,000 women versus the percentage of women in a country who live under liberal abortion laws. For example, find the point representing Oceania. Oceania, about 75% of women live under liberal abortion laws, and there are about 16 abortions per 1,000 women. Pause the video and see if you can answer the following. Then come back and we will look at them together. Based on the plot, what are the explanatory and the response variable? The explanatory variable will be located along the x-axis, and in this case is the percentage of women aged 15 to 44 living under liberal abortion laws. The response variable will be located on the y-axis. In this case, it's abortions per 1,000 women ages 15 to 44. Give the percentage of women living under liberal abortion laws and the number of abortions in South America. Highlighted here is the point representing South America. Looking to the x-axis, we can see that approximately 11% of women aged 14 to 44 live under liberal abortion laws. And looking to the y-axis, we can see that approximately 32 abortions per 1,000 women occur. Describe the strength and the form of the association in the plot. The plot moves down and to the right and is therefore negative. The strength, moderate to moderate to moderate weak would be appropriate, and the form is linear. Based on the plot, is there a pattern suggesting that as the percentage of women living under liberal abortion laws increase, the number of abortions decreases? Yes, we can see that pattern. Can we conclude that liberal abortion laws cause the decrease? Why or why not? No. We can never use a plot to determine causation. In this case, one potential confounding variable would be access to birth control. The higher the percentage living under liberal abortion laws, the higher the percentage of women that have access to birth control. And then also, higher access to birth control leads to fewer abortions.